start the last session of the day before the reception. So it's my pleasure to introduce Barak Weiss, and he's going to talk to us today about new bounds on the covering density of
lattice. Thank you very much.
Great.
So, thank you very much, Daniel, for introducing me so well and pronouncing my name correctly and inviting me to give this lecture, and to the other organizers as well. So this is, for the past few years, it's been really a pleasure for me to discover that computer scientists and electrical engineers are also very interested in lattices and have a lot of great ideas about lattices. I've been studying lattices from a dynamical point of view for a while, but now there's a lot of things going on that are bringing the people together, and so I hope the program will be a success. And I'm glad to be here. I'm also glad I had the stereotype that in a computer science center you're going to have to prepare a Beamer talk, because all the computer science talks I've been to were always kind of very nice Beamer talks. Fortunately, that's not the case because I have a whiteboard talk. So my co-authors are Or Dentlich, who is a electrical engineer, and Oded Regev, whom many of you probably know, who's a computer scientist. And what we study is the so-called covering density of the lattice. So let me define that. So K Rn, a convex body. So by that I mean it's just a convex set with non-empty interior. It doesn't have to be symmetric. And the covering density, L is a lattice. The covering density of L with respect to K, which is usually denoted with this capital theta, is the inf of the volume of R times K, such that R times K plus L equals Rn, divided by the co-volume or the determinant of L. Okay? So let's read this carefully if you haven't seen it before. So what we want to do is take our set K, dilate it, and such a way that when you center it at every lattice point, you cover space and dilate it by the smallest possible amount. And we are we're measuring things in terms of the volume. So the quantity doesn't really depend on K, it just depends on the shape of K up to dilations. We are rescaling in the denominator by the co-volume of the lattice. So it's really not a question about the co-volume of the lattice either. It's insensitive to dilations. And of course, it's also insensitive to translations, because if K covers, then so does any of its translates. So it's a geometric quantity. And some of you may be familiar with the so-called covering radius, which is an associated quantity where if you're talking about, say, a symmetric body or a Euclidean ball, you want to take the infimum over the radius of the ball. So this is a kind of a more refined, getting estimates on this is somewhat more refined because this grows much more rapidly as you increase the dimension. As the radius grows, the volume grows by the radius to the power n. So it makes it possible to look at this quantity in finer detail. But everything about this quantity can be translated into a statement about a covering radius as well. Okay? And theta, capital theta Kn is the n for these quantities over all lattices. Okay? And so to make theta small means that we're able to cover space. To make this quantity small, it means we're able to find a lattice for which the overlaps of the translates of the body K don't take up too much of the volume of the space. So in other words, for example, if K were a cube, we could take Zn. It would tile space perfectly with no overlaps, and this quantity would be equal to exactly 1. 1 is an obvious lower bound because you can't cover space. This is sort of what Noah was explaining in the beginning of his lecture. There's no way to do this more efficiently than with co-volume. Okay, so this is the definition of what we want to study. And Rogers spent a lot of time studying it, and so results of Rogers and his co-authors from the 50s, 60s, and 60s there's a, if K is a Euclidean ball, in that case, Rogers proved that this quantity is bounded by, I'm not being completely precise. Rogers was more precise than I am. But for the Euclidean ball, the covering density is somewhere between constant times n. It's not the same constant. Okay. Somewhere between one constant times n and another constant times n times the power of a log. So it's quite precise. For a general body, the upper bound that Rogers obtained was significantly weaker. To get up to constants, it's n to a power log n, so it's growing slightly faster than polynomial. Okay? And so you see that there's quite a big gap between what Rogers could prove for the Euclidean ball, and this was later generalized to a few other higher dimensional analogs of balls for other norms and other bodies with large symmetries. This bound is much, much better than this bound. So our first theorem, which I'll say over here, yeah.
The lattices that achieve this density, are they easy to describe?
No, the argument involves a probabilistic component, so their existence is proved probabilistically, but the probability, I'll say a few words about what kind of probability distribution was used by Rogers in a moment. Okay? It's not a kind of a commonly studied probability distribution. Our first theorem proves this statement. To n squared. So we improve log n to n squared, which almost matches what's known for the Euclidean ball up to the distinction between n and n squared. Okay. The second statement that I want to tell you about. So let mu n. So let's let curly ln be the space of all lattices of covolume 1. This is the space that was mentioned by Noah. I'll just write SLNR over SLNZ for a second. So let Ln be the space of lattices covolume 1, and mu n the SLNR. Than what Noah used, Haar-Siegel measure. Okay, so I don't want to scare people who are non-mathematicians, but I do want to be precise. And so on the space of all possible lattices, there's a natural topology and a natural measure. One way to think about the topology is to think about it in the language of Lie groups. So there's a canonical way of identifying an element of this quotient of Lie groups with a lattice. If you're not familiar with it, don't worry about it. It's just the space of all lattices equipped with a nice topology, and this is what Noah was alluding to. And on this space, there's a natural probability measure, which is constructed out of the so-called Haar measure for SLNR. It was constructed by Siegel, so I'm calling it the Haar-Siegel measure. Noah called it the Haar measure, although I think that's historically not the best terminology. But this is the unique measure on this space, which is invariant under linear transformations preserving volume. So there's only one measure on the space of lattices, which is natural from a mathematical point of view, in that all quantities that you measure don't depend on linear transformations. So, for example, if you're counting, I don't know, any random variable that involves counting the number of points in a ball, will be the same as the same random variable involving counting the points in an ellipse of the same volume, because you can map the ball to an ellipse. So in that sense, it's a natural measure. Okay, so with respect to this measure, it was not known, so let me write that as a question. question, what is mu n typical behavior of this quantity? So L is a lattice. It's chosen at random with respect to this measure mu n, and we want to know how big this theta k can be. And let me just remind you that theta k has an obvious lower bound of 1. With respect to this measure, its expectation is actually infinite. So you can have arbitrarily large covering volumes. And in fact, you can make them large at a rate which is sort of bigger than the measure, the inverse of the measure of very, very degenerate lattices. So in some sense, the expectation is not the correct quantity to ask about, but a specific question. Can people see if I write down here? No objections? No objections. Okay. So a question of Strombergson, for example, is the mu n probability that such that. So let me use the terminology covering radius and then explain the relationship. So covering of delta. Does this go to this go to 0 as n tends to infinity for any positive? Okay, so sorry, 1 plus delta times by 0, where so when I use volumes, everything rescales nicely, so the obvious lower bound is 1. When you use the notion of a covering radius, the lower bound is the choice of the radius making the unit Euclidean ball have volume 1, which is approximately square root of n. And so what Strombergson wanted to know was whether the probability that you're far away by a constant factor from the lower bound, whether that goes to 0 as the dimension increases. And if you sort of, as I said, covering radius problems can be translated into covering density problems. If you sort of rearrange this and think about the relation, he's basically asking whether this whether the volume grows, if you look at an exponentially increasing rate of growth of the volume, does the measure of lattices with that property go to 0 with the volume? That was his question. And we answer this affirmatively. And in fact, we show that you can do much, much better. So let me write down, and this is related to the previous question about the measure. So from my point of view, this would be the natural measure with respect to which what you should ask this question. Rogers was using a different measure, which I think is the reason it's well adapted to his method, but I don't think it's a natural measure in any sense. Okay? So let me write down our result. I'll write down a precise result, and then I'll about this problem, and then I'll explain how to understand it. So I'll call that PO2. So there are 4 constants, C1, C2, C3, C4, such that for all n, for all convex bodies K in Rn, for all numbers m in the regime n squared log n and n cubed, the probability that the covering density is bigger than m empty. Apologize for this expression. So we're giving you an upper bound on the probability with respect to this measure that the covering density is bigger than a parameter m. M is in the regime of n between n squared log n and n cubed. So corollary 1, if n equals c times n squared log n, then un, this expression, goes to 0. Corollary 2, if m is c times n cubed, this probability goes to 0 exponentially. Okay, so if you're choosing random lattices in high dimension, and you're looking at a convex body, and the convex body has volume approximately n squared, then you have very high probability of hitting a lattice for which this covers. And if you want to be extra sure, you might want this to go to 0 exponentially fast, this probability, and then you should choose your volume to be on the order of n cubed. Yeah.
So just to clarify, in terms of this delta, you're saying that delta equals 1 over n is good enough?
Yeah, delta equals 1 over n. I have to do the math here because it's even more precise because I have to distinguish between n squared and n cubed, right? So 1 over n.
Like log n
Log n
over
over
1
n.
plus log n over n with the
Okay.
constant.
Some people can do these computations faster than I can. Yeah.
One other quick question. The R naught there, would it be related to the covering radius for the ball with the random, like, the concentration of the covering radius as you vary the lattices over Ln presumably, is it?
I didn't understand the question.
So instead of defining R naught by volume,
Good.
wouldn't it be better to define it as the blow up of the ball you need to take to get the covering radius to cover space plus a lattice,
For
random lattice?
a random lattice.
I mean, if it's concentrated.
I mean, I choose my R naught just to be the obvious lower bound. So R naught is the simple lower bound given by volume on the covering volume, irrespective of the lattice. That's my normalization. I don't know if I answered the question. Okay. So this is like usually called R effective, but the engineers call this the R effective radius, the effective radius. So the proof involves a couple of steps, and the surprising thing is, as I told you, we have an electrical engineer on the team, computer scientist on the team, and I'm a dynamicist. The new tool comes from combinatorics, which is a field that none of us are experts in, so that's quite nice, actually. So it's something called the discrete Kakeya problem. So I'll tell you what the discrete Kakeya problem is, and I hope to have enough time to really show you basically the proof, not of theorem 2, but of theorem 1. So from here on out, I'll just give you our new proof, our proof of theorem 1. And then if people ask questions, I can tell you more about theorem 2. What is a Kakeya set? What is a discrete Kakeya set? And I need a definition about it. Discrete Kakeya set of rank R. Definition. So K in F e to the n is a discrete Kakeya set of R is for all S. Okay, I'll just write everything down and then I'll explain. So we're working in the finite field FP. P is a prime, or it could be a power of a prime. And we're looking at a subset. This is a set which has p to the n elements, and it's a vector space. And so this Grassmannian is all the r-dimensional subspaces in this vector space. So for starters, just think of r as being equal to 1, so that if r is equal to 1, this is all lines in this vector space. And we're saying that a set is called a discrete Kakeya set if it contains a translated copy of each plane of the dimension r. So if in the case of lines, it contains a line in every direction. And there's been a lot of activity. Obviously, the bigger a set is, the more likely it is to be a discrete Kakeya set. And so people are interested in getting bounds on the possible sizes of Kakeya sets. They want to say that if a set is a Kakeya set, it can't be too small. And there was a big breakthrough regarding the size of Kakeya sets, and associated mainly with the name of Dvir about 10 years ago. But there's been a lot of subsequent work. And so I'm going to state a theorem of, the theorem that we need is not due to Dvir, it's due to KLSS, which is Koparty, Lev, Saraf, and Sudan from 2011. And what they proved is the following. We care about the case of rank 2. And so they proved that the cardinality of Kakeya set is at least e to the minus n over p times p to the n. P to the n is the size of the entire set. And we're going to be interested in the regime where p and n are approximately the same. So this will come out to be a constant. So what they're saying is that a Kakeya set of rank 2 should occupy at least a constant proportion of the entire discrete vector space. And let me, since I want to use it in a few minutes, I'll record a corollary of this. If you have a set which is big enough so that its complement cannot be a Kakeya set, I'll just write it down again. If you have a set which is so large that its complement can't be a Kakeya set, that means that you can find a two-dimensional subspace so that no matter how you translate it, it has to intersect that set. In other words, it can't be contained in the complements. Okay, so let's just keep this in mind. And just think about this in the case where n is equal to p, so this just becomes 1 minus 1 over e. Yeah?
5.
Oh, well.
Well, or I mean, no.
Okay.
I'll stay.
Okay, people, probably I'm going to end up not managing to give you the proof, but hopefully I will get the idea.
Oh, it's 45 minutes. My bad. So I lied.
Don't lie.
Yes, thank you.
So how much time do I have?
Longer.
Let me thank the organizers for inviting me. So the second, this is like, let's call this ingredients for the proof. And this was the first ingredient, discrete Kakeya problem. And this is, the reason I'm highlighting this ingredient is that it wasn't around when Rogers was doing his work, and the bounds that we're discussing had not been improved since Rogers, so for around 50 years. The next two ingredients that I want to tell you about are ideas basically which can be found in Rogers. So the second ingredient is an idea of Discretization. And the idea here is that if you can cover, if your set is convex and it covers maybe not the entire Euclidean space, but it covers a set which is kind of a dense grid, then you can slightly make it slightly larger, and then it will cover. So the most efficient way to state that is in terms of the quotient lattices, quotient tori. When you have a lattice in Rn, you can divide by the lattice to get a periodic set, a torus, and I'll state the theorem in the language of tori. So we have two lattices, L1 and L2. L1 is contained in L2. We have a convex body K in Rn, and we have a positive parameter rho. Let me draw the diagram. Here's Rn. Rn maps to the first torus, which is the quotient of Rn by L1. And this maps further into the quotient of Rn by L2. So remember that L1 is contained in L2. So we have this map, these two maps. And let's call this first map pi1 and this map pi2. And we make two assumptions. The first is that pi1 of k covers pi2 inverse of 0 for some 0. And downstairs torus. And let me explain these two hypotheses. Let me write down the conclusion first. The conclusion is that the lattice L1 will give you a cover of space with your convex set K as long as you inflate K by a small factor. Think of rho as being a small number. Okay, so this is what you want to achieve. The way so you're trying to cover using L1. You should think of L2 as giving you this set, pi2 inverse of x0, which is some kind of nice grid, regular grid, sitting inside this torus. Okay, so if I draw the picture, if this is the first torus, I can take a point in the quotient and pull it back, and I get a nice regular set like this inside the torus, which is the preimage of some point under this projection. It's a periodic set. And so the first assumption is that the projection of K covers this discrete set of points. And the second assumption is that this set K projected all the way down here, measured with respect to the natural probability measure, the Lebesgue probability measure on the downstairs torus, occupies at least half of space. When you make these two assumptions, you get this conclusion. Okay, so this is not a difficult fact, which is due to Rogers, essentially. The next ingredient.
So, sorry, what? It's on rho?
Rho is a parameter, but you need rho to be big enough for this to happen.
Ah, the row is there. Yes,
Yeah.
yes. Okay.
The third ingredient is a difficult piece of work done by Rogers and Wolfgang Schmidt in the 50s and 60s. So, I'll just call this the Rogers-Schmidt down. That's this is our name for it, and so let me state it. So you have again a lattice, but we're going to be varying the lattice. So in a moment, so L is a lattice. Whenever I have a lattice, let's denote the quotient torus Rn divided by L by T of L, and ML is the normalized Lebesgue measure on this torus. And we have a set which we can call J a subset of Rn. All it needs to be for this theorem is measurable. It doesn't matter whether or not it's convex. And what we're interested in is what happens when you take this set in Rn and project it to this torus TL. And L varies. And for different L, this projection is going to cover either most or few, a small part or a big part of the quotient torus. Okay, so imagine a Euclidean ball, say of volume 2. If you're taking Z2, it's going to probably cover everything. But if you're taking a lattice with a very short vector and a lattice with a very long vector, there's large open holes inside, and it's not going to cover much. And so this is a random variable. So the random variable is denoted by epsilon in Rogers notation, and this is the definition. Pi L is the projection. Okay, so 1 is the total area. Pi L of J is what's covered by the projection of J. We're measuring how much is covered by the projection of J, and then we're subtracting. So this is the proportion of the torus missed by the projection of J. Okay? And I'll state it over here, but I'll state the corollary over there because it's not really crucial to get, well, yeah, let me state it over here. So, Rogers, I guess. Take a set V whose volume is growing linearly with n at most, and you take a parameter kappa, then the measure, with respect to this natural measure, of the lattices for which the amount you miss is bigger than kappa times e to the minus the volume. This is less than 1 over kappa plus C2 into the C2 over kappa V minus C1. Okay, so let's look at this formula for a little bit. So basically, this is telling you that the threshold is e to the minus v. So think of, you have a fixed set J. You're projecting it onto tori for a random torus. And just think of this as a kind of a completely independent event for every point, whether or not it's going to be hit or missed by this projection. And if you sort of use that heuristic, you're sort of going to reach the conclusion that most points are going to be hidden. The probability that you're going to be missed is roughly e to the minus v, where v is the volume. And so what's the probability of going above e to the minus v by a constant factor kappa? It's decaying with kappa. And there's an additional term. Now, if v is close to the critical, there's a bound on v here. V can't be very, very large. Your set has to be fairly small. Okay? So if v is close to being the maximal size allowed in the theorem, then this term starts becoming large. But if, say, v is constant, say, or growing smaller than linearly in n, then this term becomes irrelevant, and the probability is going to 0. Okay? So this is a technical statement which was quite hard to prove, and I think Rogers was quite proud of it. If you read his introduction to his book, you'll see. And let me just state a corollary here for later use. So I'm going to use it with v equal to 2, kappa equal to e. The probability that probability that the amount that gets missed is bigger than 1 over e is less than 1 over e plus some little o of n, something going to 0 with n. Okay? So in other words, we take a set, its volume is 2, which is slightly bigger than 1, and we take a large enough dimension, then most points in the sense that all but 1 over e of points are going to get hit. And I chose this 1 over e because it matches this 1 over e. Remember that p equals n for our application. Okay, so this 1 over e is going to beat this 1 minus 1 over e. So now I've set up all that I need in order to sketch the proof of the, maybe I'll leave this discretization hypotheses and conclusions here as well. And start the proof over here. No lies this time. How am I doing on time?
Now you really have 5 minutes.
Okay, so I'm going to sketch a proof of theorem 1. So I'm trying to show you why if you have a compact set whose size is growing like n squared, or constant times n squared, you can find a lattice so that together they cover all of space. And I want to use the discretization lemma, so I'm going to try to reach the conclusions of this discretization lemma, but I haven't figured out yet what L1 and L2 are. So I forgot to, let me keep the notation that I had before. So there are 2 lattices in the background. L1 is contained in L2. And I'm going to do this in 2 steps. In the first step, I'm going to find a lattice of covolume 1, which is given to me by Rogers, so that the projection of my set K onto the quotient occupies most of space, but definitely not all of space, and definitely not enough so that it covers a grid like this. And then I'm going to find another lattice bigger than it, for which it actually, this hypothesis 1 here can be verified, and that's where K will come in. So let K. And in the statement that I want to prove, K is a convex set of volume n, but I'm just going to start with a convex set of volume 2. So just think of your convex set and rescale it so that it has volume 2 for now. So let K be convex of volume 2. The reason I chose 2 is because that's what I wrote over there in the second corollary. By this corollary, let's call it corollary 2. Let's call it corollary 1. By corollary 2, there exists a lattice L so that epsilon KL is less than 1 over E. So in other words, the projection of L onto the quotient, the projection of K onto the quotient of space by L misses less than 1 over E of space. Let's take P to be a prime equal to N. Okay, so of course it's a joke, not all N's are primes, but we can take an N which is, we can take a prime which is close to N, so say between N and 2N or something like this. It'll only affect constants. So I'll just assume that N is prime if you like. And think of the vector space, the discrete vector space, Fp to the n as the projection of 1 over P times L, and this lives in Rn over L. So pi is the projection from Rn to Rn over L. And we divide the lattice by P, meaning we make it smaller by 1 over P in each direction we have, and we project. So we're getting P to the n regularly spaced points inside the lattice. So this would be like an example with P, I don't know, around 5 or 7 or something like that in 2 dimensions. So this is a discrete net, and it's not necessarily satisfying this quantity it gets a complete translate of it. Now I'm talking P2 inverse of x0 means you're allowed to translate this around in the torus. Well, let's translate it around so that the number of points that get hit are the average number of points that get hit. So there exists an x0 such that I of 1 over e to the n plus x0 is proportion of this that is in I of k is bigger than 1. Let me continue over here. Corollary 1, the discrete Kakeya assumption, I can find a two-dimensional subspace over Fp, again, where I think of this projection as a copy of Fp to the power n. And in this Fp to the power n, I apply the Kakeya, and I can find an element of the two-dimensional Grassmannian which intersects every line. So for all x, again, x plus s intersect the projection of k is non-empty. So now what I'm going to do, I haven't defined L1 yet. Now the definition of L1 will be I'll thicken L by adding S to it. Okay? Define L1 equals L plus S. Okay? S is some elements, some subspace, some two-dimensional subspace of elements in this projection of this subspace. It's a subgroup in this quotient group. So I can just add it to L and get a lattice. And the index of this lattice is exactly the size of S, which is p squared. So the co-volume determinant of L1 is p squared. Now, if you think about what I've done, because of this claim, what I've done is I've added points to my lattice so that in every direction in my lattice, I'm going to now hit the image of k at least once. So that means that when I project further into the quotient by L, then the set k is going to satisfy exactly this hypothesis. Okay? So I haven't said what L2 is. Sorry. L2 is 1 over p times L. Okay? So if you think about this for a moment, you'll see that with these choices, both of these hypotheses, well, I've told you how to verify this hypothesis, which is the main hypothesis. With these choices, this hypothesis will hold, and so will this hypothesis if I choose rho to be 1 over p. So with rho equals 1 over p, 1 and 2. So you can convince yourself that I haven't lied to you, and it just follows from this choice of L1. Okay? And that's sort of the punchline of the proof. And now what we're getting is this. Now, K was of covolume 2. I've made it larger by just a constant factor. But I have to rescale everything by a factor of p squared, because that's the covolume of L1. When I do that, nothing happens to 2 times rho is 1 over p. So 1 over p times rescaled by p squares only affects the volume up to a bounded amount. So I have covered, if I rescale the picture, you'll see that I've covered space by a body which is a dilate of k and has a volume constant times n squared. And that's basically the proof. Do I have 1 more minute or not?
Sure.
Thank you. So just one word about the proof volume of theorem 2. So theorem 2 is about this Haar-Siegel measure. In order to prove theorem 2, you have to run through the same steps and check that what you're doing works for a random choice of L. And this is not a random choice of L. We used Kakeya. So we have to upgrade Kakeya to something called epsilon Kakeya sets, which is talking about most choices of these S's, of these subspaces S. And we also have to analyze this Haar-Siegel measure. And the point about Haar-Siegel measure is that it has the following property. If you randomly choose a lattice according to Haar-Siegel measure, and then randomly choose a sublattice of a fixed index, or a superlattice of a fixed index, in this case we chose L1 to be a superlattice of index p squared, so it contains the original lattice and lattice p squared. If you make that second choice uniformly, you're still working with the Haar-Siegel measure, properly rescaled. It has that naturality property. And so what we have to do in order to prove the second theorem is to sort of run through the whole argument again with a souped-up version of the Kakeya problem, which actually is another one of our contributions. It wasn't in the literature, and this understanding of the Haar-Siegel measure to get theorems. Okay, thank you for your attention. Yeah.
So the quadratic behavior for the upper bound is for large n.
Right. Right.
Because of the probabilistic approach.
Yeah.
So this is very similar to what we do in information theory. N is asymptotic. Can we say something about finite n? Theory, can something hold that finite n?
We didn't. I think the answer is yes. I mean, our constants are quite explicit, and so are Rogers constants. If you reach Rogers, it's amazing how explicit they are. The super explicit constants. So I believe the answer is yes. One would have to carefully track the constants and how they, you just need some numbers to be bigger than other numbers, and that's true asymptotically. So I don't know when that will kick in. I think it will kick in not too large an n, like on the order of 50 or 100, but I'm not 100% sure. Yeah.
So the quadratic appearance in theorem 1 is coming from the fact that you're working with rank 2.
Exactly.
Is there any hope? Is it known, the rank 1 Kakeya?
So the rank 1 Kakeya statement is, of course you're asking about our frustration, so let me tell you about our frustration. So definitely we wanted very much to match Rogers and to reprove Rogers and to match Rogers' framework, and that would have meant working with the Kakeya problem in dimension 1. And then dimension 1, we're kind of off by constants, so it's never nice to beat constants by constants because you never know where the mistake might be lurking. At the moment, not only we have constant coming from Rogers and we have constants coming from the experts on the Kakeya problem. If we could improve on Rogers' constants, that would make it possible. And as you could do it, of course, you could improve. In the Kakeya literature, a lot of their estimates are tight. So the answer is we're thinking about it, but we don't have an answer at the moment. And I guess it's an interesting problem as to whether the truth is closer to n or to n squared, and we don't know at this point.
So what's the issue? So for rank 1 Kakeya, the sets, the lower bound is too weak?
Yeah.
By like how much? By a lot?
By a constant.
I see.
By a constant in n. And the constant is around 100. That's all. But we can't do it there.
Wait, so where does the n squared finally come from?
We've dilated by p. And so L1, so we had the volume of the set K was constant, but then we dilated the picture using the co-volume of L1, which is p squared because for L it was 1, and then we added a two-dimensional we added p squared number of points.
Right.
So now it becomes p squared, which is essentially n squared in our normalization, and that's the n squared.
Okay.
Yeah.
What does your theorem 2 say about the last minimum of a random lattice?
The minimum of a random lattice?
Last minimum.
Lambda n. Lambda n.
Lambda n. Do we improve any results about? So I guess you could, of course, apply Banachek. I don't know if we found it. I'm not sure. Right. So lambda n is lambda. I'm sorry. No, lambda. The only thing I can say, which might be useful information, is that the Siegel-Haar measure is invariant under taking duals. Right. So if you have some set of large volume, and so is the set of duals. So wait, so lambda 1 is connected to the covering radius by Banachek, right? So I don't know the answer to your question. But people have studied the behavior of lambda, all the lambdas.
But the first lambda for fixed k, I mean for fixed k, the limit distribution of lambda k is pretty much known, but not for the
Okay, we can discuss. I think that's not completely accurate. There's been some literature on the regime where k grows with n.
but not until n, right? I mean only for
Let's discuss.
something like
All right. Is there no more questions?